Hey, what's up, my data elites? You are listening to the NB Nexa Show, the podcast where we take complex topics and make them captivating. I'm Nabanita, and today we are diving deep into a critical but often underestimated aspect of machine learning: model evaluation. Whether you are working on a simple classifier or a state of art neural network, the way you evaluate your model can make or break your project. Let's explore the matrices and techniques that go beyond just looking at accuracy. Why is model evaluation important? Model evaluation isn't just about knowing how well your model performs, it's about understanding how it performs and why. It's the lens through which you assess your model's ability to generalize to unseen data and identify its strengths and weaknesses. So let us start by talking about key matrices for classification. There are four common terms in confusion matrix you need to know. 1. True positive. Those are correctly predicted positive cases. 2. False negative. Model predicted negative, but the actual case was positive, which is a misdetection. Next, third is false positive. Model predicted positive, but the actual case was negative. False alarm. Okay. Next, four is true negative. Correctly predicted negative cases. While accuracy is the go to metric, which is calculated by the sum of true positive and true negative over the total number of predictions, it is not always enough. Imagine a dataset where 95% of emails are non spam. A model that always predicts non spam will have 95% accuracy, but it's useless for detecting spam. That's why we use other matrices like precision, which is also called positive predictive value. How many of the predicted positive instances were correct? And the formula to calculate precision is true positive by true positive plus false positive. Next is recall. It is also known as sensitivity or true positive rate. How many actual positive instances were correctly identified? The formula to calculate recall is true positive by true positive plus false negative. Next, we have F1 score. It is the harmonic mean of precision and recall, balancing the two when you cannot prioritize one. Next, we have specificity, the true negative rate, measures how well the model avoids false positives. The formula is true negative by true negative plus false positive. We also have ROC-AUC curve, which measures the trade-off between true positive and false positive rates, giving a broader view of performance. For advanced tasks like multi-class classification, we use metrics like macro average F1 score or weighted precision to account for class imbalances. Next, let's talk about metrics for regression. In regression problems, common metrics include mean squared error and mean absolute error for measuring prediction accuracy. R squared to explain how much variance in the data your model captures, but at an advanced level, using metrics like mean absolute percentage error or logarithmic loss might provide better insights for specific problems. As we are discussing about several matrices for model evaluation, let us also cover cross-validation. It is a gold standard for evaluating model robustness. Splitting your dataset into training and testing isn't always enough. Techniques like k-fold cross-validation divide the data into k subsets, ensuring every data point gets used for both training and testing. For time series problems, method like rolling window validation ensures temporal consistency. Sometimes we need to think beyond metrics, something like explainability and interpretability. Metrics alone can't tell the full story. Techniques like shape values or lime allows us to understand how features influence predictions, making model evaluation more actionable. In critical domains like healthcare or finance, these tools are indispensable for building trust in your model. There are some common pitfalls in evaluation as well. Even advanced practitioners can fall into traps like data leakage, where information from the test set can leak into training process, and also overfitting to the validation set, which makes your model appear better than it is. Addressing these issues requires rigorous pipeline design and often separate holdout datasets for final evaluation. Model evaluation is both an art and a science. It's not about just choosing the right metrics, it's about understanding your data, your model, and your use case. By mastering these principles, you will not only build better models but also ensure they succeed where it matters most, the real world. That's all for today's episode of Model Evaluation in Machine Learning. I'm Nabanita and don't forget to subscribe and I will see you next time for more insights into the world of AI. Stay a curious kitty and keep learning.